There's a specific kind of fatigue that comes with cataloguing. Not the dramatic exhaustion of discovery, and not the kind that gets written about, but the low, flat tiredness of doing the same careful thing over and over in the dark. Measuring, recording, moving on. If you've ever done any kind of data work, any kind of tool, you know the feeling. The work has a rhythm. It asks you to stop thinking and just count. That's roughly what Robert Kirshner and his colleagues were doing in 1981. Not roughly, exactly. They were doing a redshift survey, measuring how fast galaxies were moving away from us, which is the same as measuring how far away they were, which is the same as building a map of where things were. The survey covered galaxies brighter than a certain magnitude, are approximately 16.3, and they measured redshifts across 3 separate fields in the sky, each field separated from the others by about 35 degrees. 133 redshifts total. It was methodical work. The kind of work where someone has already told you what you should find before you find it. What you should find, given the distribution of matter in the universe, is a smoothish peak. Galaxies clustered around certain distances, thinning out at the edges, the whole thing looking roughly like what you'd expect from a universe that had been expanding for 10 billion years and filling in as it went. The expected peak in their data was near 15,000 kilometers per second. That's the redshift velocity, the speed at which galaxies in a given volume would be receding. The number that tells you how far away they are. One galaxy, out of 133 measured redshifts, only one was found in the 6,000 kilometer per second interval centered on that expected peak. One, I keep coming back to that, one galaxy where maybe 100 were anticipated. The number is so clean that it almost sounds made up, not because it's dramatic, but because drama usually has more texture than this. This was just a flat line where a curve was supposed to be. A column in a tapis that came out nearly empty. They published the paper, Kirshner, Lonelier, Schechter or Jechtman. In September 1981, in the astrophysical journal Letters, the title was "A Million Cubic Megaparsec Void in Boötes," and that question mark is doing real work. It's not rhetorical, it's not humility for the sake of humility. They genuinely weren't certain what they'd found. A void that size wasn't something the models of the time had reason to predict. So the question mark meant, we measured this, and we're telling you what the measurement implies, and we're also telling you we know how strange it sounds. Redshift surveys were, at that moment in the early 1980s, the primary way of building three-dimensional maps of the cosmos. Before this era, galaxy maps were flat. 2 dimensions, right ascension and declination, a projected image of the sky without any sense of depth. Redshift added the 3rd dimension. If you know how fast a galaxy is receding, you know, roughly given assumptions about the expansion rate of the universe, how far away it is, and with enough redshifts you could build a map, not a photograph, a structure map, a map of where the mass actually was. This was transformative work, and it was happening at multiple institutions simultaneously. The Harvard-Smithsonian Center for Astrophysics had a major survey underway. Kirshner's team was part of that broader effort, not racing exactly, but certainly not the only group doing this kind of thing. It was one of those periods in science where the tools had finally caught up to the questions, and everyone who had access to a telescope and a spectrograph was pointing it at the sky and counting. The expectation going in was that the universe would turn out to be lumpy but bounded, superclusters here, smaller clusters there, voids of some kind certainly. But voids of a reasonable size, maybe tens of millions of light years across. The kind of void that makes sense structurally as the space between walls of galaxies. The cosmic web was already being guessed at vaguely. But nothing in the theoretical framework of 1981 had prepared anyone for an empty region roughly 250 million light-years across, which was the initial estimate, later expanded with almost nothing inside it. And here is the strange part, or one of the strange parts. The void wasn't found by looking for voids. That's not what the survey was designed to do. Kirshner's team was mapping the plenitude, cataloguing what was there, and the nothing showed up anyway. Like a pothole you discover because you drive into it, not because someone warned you it was there. I want to be careful here about what the word discovery means in this context. It's tempting to frame it as a eureka moment. The data arrives, the absence announces itself, someone gasps. That's not really how it works. The data came in incrementally. Redshifts were measured one galaxy at a time, plotted, compared. The gap would have become visible as a pattern, not as a single revelation, more like a growing suspicion. The histogram starts to look wrong. You check the fields again. You wonder if something's off with the instrumentation. You look at the numbers from the 3 separate sky fields and notice that all 3 of them show the same gap, a 6,000 km per second absence. The same absence, in fields separated by 35 degrees. That's when it stops being an instrument problem. 3 independent lines of sight. Same gap. Same scalance. That's the moment, I think, where the question mark in the paper title was born. The survey rooms of the early 1980s are worth pausing on just briefly, not because they're romantic, but because they're grounding. Spectrographs were large, physically unwieldy instruments. The data often came out on the photographic plates before being digitized. It was slow work, the kind of work where you might have had coffee going cold on a desk somewhere nearby, under fluorescent lights, the low hum of equipment filling the room. Astronomy was less ethereal than people imagine. There's something I find clarifying about this. The universe turns out to be mostly empty, a point we'll come back to in some detail, and the humans who first detected its most spectacular emptiness were sitting in an ordinary room, doing ordinary paperwork, in the usual mild discomfort of a late shift. The result, when Kirshner's team published it, was not immediately accepted as a settled finding. How could it be? A region 1 million cubic megaparsecs in volume with almost no galaxies. That wasn't just unexpected, it was almost structurally implausible given what was understood about how the universe formed. The standard picture of cosmic structure at that time leaned toward a universe that was, at the largest scales, more or less uniform. Lumpy. Yes, but not this. Not a spherical absence the size of what they were describing, and so the scientific community did what it usually does with surprising findings. It looked for the error. Maybe the fields chosen were anomalous. Maybe the survey wasn't deep enough and the galaxies were simply fainter than the detection threshold, present but invisible. Maybe the 3 fields weren't as representative as they seemed. These are reasonable objections. They're not dismissals, just good practice. Extraordinary claims require the usual additional scrutiny, and a void this large was certainly extraordinary. What happened next, though, was that subsequent surveys kept going back to the same region, and they kept finding the same thing. In 1987, Moody, Kirshner, McAlpine and Gregory confirmed 8 galaxies within the void. Not 1,000, not 100, 8. In 1988, Strauss and Huchra found 3 more. In 1989, Aldering and colleagues identified 15 additional galaxies by Ying, and also noted something strange about their arrangement. They were clustered in a roughly tube-shaped region running through the center of the void, not distributed throughout it. By 1997, the total count had reached 60 known galaxies across the entire volume. 60! Where the math suggested 2,000 should be, The question of why comes later. There are answers, partial ones, working ones, the kind that cosmology usually produces, and they involve how voids form, how smaller voids merge, how the universe's expansion has a way of evacuating emptiness even further. We'll get to those. But it's worth staying here for a moment in 1981 in the question mark. Because one of the things that gets lost when we talk about the history of a discovery is the genuine not knowing that preceded the explanation. Kirshner and his colleagues didn't title their paper with a question mark because they were being coy. They titled it that way because the sound they didn't know. The void was real, what it meant, whether it was a statistical fluke, a measurement artifact, a genuine hole in the cosmic structure, that wasn't settled. Not yet. It still isn't entirely, which is a strange thing to say about something we've been studying for over 40 years. But the Boötes Void has a way of resisting complete comfort. You can explain its existence within the current best model of cosmology, and the explanation holds. But it holds at the very edge of what the model comfortably absorbs. That edge is where most of the interesting things in physics live. The paper ran 4 pages. 4 pages to describe something 330 million light-years across. There's a certain proportion there that doesn't resolve neatly, the smallness of the description against the scale of the thing being described. But maybe that's not unusual. Maybe that's just how it always goes, in science and otherwise. The thing exists at a scale that language wasn't built for. You write down the numbers, you publish the question mark, and the universe stays the same size it always was, indifferent to the difficulty of the notation. 60 galaxies, in a region where 2,000 should be. The numbers have had 40 years to settle, and they still feel a little wrong when you hold them together. Not wrong like an error. Wrong like something that needs more time than we have to fully take in, and somewhere inside that accounting problem, somewhere in the gap between 60 and 2,000, the actual strangeness of this place begins. 700 million light-years. Say it plainly and it means almost nothing. The number is too large to land anywhere useful in the mind. It just sort of hovers, technically present, actually inert. We're good with distances we can drive. We're decent with distances we can fly. Anything beyond that starts to lose the quality of distance and becomes something closer to a label, a tag attached to an object so we can refer to it without having to understand it. But there's a way into this number. It takes patience. Light travels at roughly 300,000 kilometers per second. Not approximately, roughly. Because even that number carries some wobble depending on the medium it's moving through, though in the vacuum of intergalactic space the wobble is negligible and we can treat it as fixed. 300,000 kilometers per second. In 1 second, a photon crosses distance that would take you, driving at highway speed non-stop, about 32 years to cover, in 1 second. Now hold that for a moment. Let it do something to your sense of scale before we go further. In 1 year, light travels about 9.46 trillion kilometers. That's a light year. A single light year. The nearest star to our Sun, Proxima Centauri, sits about 4.24 light years away, which means the light arriving from it right now left before most people reading this finished high school. It's genuinely close, as cosmic distances go. The closest thing to a neighbour our solar system has, and it is, by any human measure, unimaginably far. The centre of the Boötes Void is 700 million light-years away. That light, the light from anything sitting at the centre of that void, if anything were sitting there, has been travelling since before complex life on Earth existed in recognisable form. Before the Cambrian explosion, before eyes, before anything with a spine, It set out when this planet was populated primarily by microbial mats and shallow seas, and the very first organisms that were beginning slowly the long experiment of multicellular existence. That light has been crossing empty space ever since, and it's just arriving now. I find this genuinely hard to hold, not in an awestruck hands raised to the sky way, but in a specifically cognitive way, the way a wrong-sized tool feels in your hand. The mind reaches for the distance and finds nothing to grip. It's not that 700 million light-years is incomprehensible because it's large. It's incomprehensible because the duration embedded inside that distance has no human reference. 700 million years is longer than the history of visible animal life on this planet. It is, in the most literal sense, deep time wearing the costume of distance. There's a concept in cosmology, simple once you sit with it, called look-back time. When you observe an object at a certain distance, you're not seeing it as it is now. You're seeing it as it was when the light left. Observation is inherently archaeological. Every telescope is, in a precise and non-metaphorical sense, a time machine, not forward, only back and only in the specific direction you point it. At 700 million light-years, the look-back time is 700 million years. The Boötes Void, as we see it, is 700 million years old. Or rather, the data we have about it is 700 million years old. What it looks like now at this moment is unknown to us, causally unreachable. We can extrapolate, and cosmologists do carefully, using the physics of large-scale structure evolution, but we cannot observe it. The light from its present state won't arrive for another 700 million years. This is one of those facts that sits quietly in the background of all cosmological observation and rarely gets the attention it deserves. We are not mapping the universe as it is, we are mapping the universe as it was at many different moments, all overlaid into a single image we call the observable cosmos. The map is real, the data is real, the universe inside the map is history. Here's the thing that caught me off guard when I first understood this properly. Sitting with the diagram in a paper that I'd printed out and was reading at a desk that smelled faintly of the takeout I'd had an hour before, the Boötes Void being at 700 million light-years is actually not that far, by cosmological standards. The observable universe extends to about 46 billion light-years in all directions. The Boötes Void is sitting at roughly 1.5% of that. It is, relatively speaking, practically local, close enough that the surveys that found it used optical redshift measurements of individual galaxies, not the exotic instruments required for the very distant universe, just careful spectroscopy and a lot of patience, which makes the emptiness harder to explain away. The further out you look, the more the data thins. Fewer surveys, more uncertainty, the instruments reaching their limits. But the Boötes Void sits inside the part of the universe we know reasonably well. It has been mapped with multiple surveys, at multiple wavelengths, by multiple independent teams. Its emptiness is confirmed not once but many times over. There is no version of this where the void is an artifact of incomplete observation or a gap in survey coverage. It's there, 700 million light-years away, and clearly, persistently, unmistakably empty. What does 330 million light-years of diameter mean physically? Let's try it from the inside out. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years from the Milky Way. That distance, 2.5 million light-years, feels vast. It's the number used to illustrate cosmic scale in almost every introductory astronomy context. It's the closest thing we have, and it is brutally far. The light you see from Andromeda with your naked eye on a dark night left before Homo sapiens existed. The diameter of the Boötes Void is 330 million light-years. So the distance to Andromeda, that number we use to convey the enormity of space, covers less than 1% of the Boötes Void's diameter. You could stack 132 Andromeda distances end-to-end across the void. You could take our entire local group of galaxies, the Milky Way, Andromeda, the Triangulum Galaxy, and the dozens of smaller satellites, the entire gravitationally bound neighborhood we belong to, spanning roughly 10 million light-years, and fit it inside the Boötes Void 33 times, lengthwise, in a single direction. The Virgo supercluster, which contains our local group, which contains our galaxy, which contains our solar system, which contains everything you have ever directly experienced. That entire structure is about 110 million light-years across. The Boötes Void is 3 times wider, 3 times wider than the supercluster that contains us. And here is the thing I want to sit with for a moment before moving past it. This structure is not an anomaly in the sense that something went wrong to create it. It is an anomaly in the sense that something went very thoroughly right, from the void's perspective, for a very long time. The physics that produces voids is real. The process is well understood, at least in its broad strokes. What is not well understood is why this particular void is so large, so empty, so old-looking. It exists within the current best model of cosmological structure formation, the way an outlier exists in a dataset, not violating the rules exactly, but sitting at the far end of what the rules allow. The model says voids can form, voids can grow, voids can merge. The model does not say with much confidence voids can get this big, this empty, within the time available since the Big Bang. Some argue it can, some argue the numbers barely work. It barely works is not the same as it works cleanly. And the Boötes Void at this distance, this size, this age, it has never quite settled into the comfortable category of fully explained. The light from its edge arrives here, on this planet, having travelled 700 million years, and it tells us, there is very little where I came from. That's all it says. That's all any light can say. Here is where I left. Here is what it looked like when I left. Here is how long ago that was. What it looked like is mostly empty. What it looks like now we cannot know yet. And what that emptiness means, how it formed, why it persisted, what it says about the early universe and the physics that shaped it, that's where the story actually lives. Not in the distance exactly, in what the distance contains, or rather in what it doesn't. Just let that sit there. Not as a small number, though it is, but as an answer to a question that was expecting something else entirely. The question being, how many galaxies should occupy a spherical region of space 330 million light-years across, given everything we know about how matter distributes itself across the universe? The answer, worked out from the average density of galaxies in the observable cosmos, is somewhere around 2,000. That's not a precise calculation, and cosmologists will hedge it depending on the survey and the methodology, but the rough figure holds. A region this size in a universe that looks like ours should contain roughly 2,000 galaxies. What's in the Boötes Void is 60. There's a specific kind of cognitive dissonance that comes from a number being technically correct and still feeling wrong. Not morally wrong, just structurally wrong, the way a sentence sounds fine until you say it aloud and something in the rhythm doesn't land. 60 is correct, 60 is confirmed. Multiple independent surveys over multiple decades have found, within the Boötes Void, approximately 60 galaxies. The number is not preliminary. It is not a lower bound waiting to be revised dramatically upward. It has been 60, give or take a handful, for a long time now, and 2000 is what should be there. That gap, 1,940 missing galaxies more or less, is the thing I want to sit inside for a moment, because I think we move past it too quickly usually. We say surprisingly few, or almost empty, and the brain files it under unusual cosmic fact and moves on. But the arithmetic doesn't care about how quickly we move past it. The arithmetic just sits there, being what it is. Let's try to make 2000 galaxies concrete, because I think abstraction is letting us off the hook. Our own Milky Way is a galaxy. It contains somewhere between 100 and 400 billion stars. The uncertainty in that number is itself staggering. But take the lower bound and run with it. 100 billion stars, each one a sun, many of them with planets. Some of those planets almost certainly in conditions that could, in principle, support the kind of chemistry that led to us. One galaxy. One. Now multiply that by 2000. That is what should be in the Boötes Void. 2000 galaxies, each containing hundreds of billions of stars, each of those stars a gravitational anchor for its own small system of orbiting matter. The sheer density of potential contained in 2000 galaxies is genuinely hard to hold in the mind without it slipping. What's in the Boötes Void is 60, which means the void contains, in the crudest possible terms, about 3% of what should be there, not slightly less, not meaningfully below average, 3%. If you opened a bag of rice and 97% of the grains were missing, you'd look at the bag differently. You'd assume something had gone wrong at the factory, or that the bag had been open for a long time, or that someone had taken most of it. Some explanation would occur to you immediately, because 3% is not close to 100. It is not in the neighbourhood. The Boötes Void is not in the neighbourhood. Here's where I want to be careful, and I'll admit I've written this section twice now, because the first version slid into something more dramatic than I meant it to be. The missing galaxies are not missing in the sense that they existed and then vanished. That's not what the physics says, and it would be wrong to imply it. The Boötes Void doesn't appear to be a region that once had 2000 galaxies and then lost them. The current leading understanding is that it's a region where galaxy formation was suppressed, where the initial density of matter was so low that the usual machinery of gravitational collapse never got adequate traction. Matter didn't accumulate into structures the way it did elsewhere. The galaxies that should have formed didn't form, which is its own kind of strange, because didn't form is different from disappeared. It means the Boötes Void is not an aftermath. It's more like a place where a certain process simply declined to run, where the usual sequence of events, the slow clumping of matter, the ignition of stars, the coalescence of galaxies, stalled out somewhere near the beginning and never recovered. The 60 that are there. Let's talk about them briefly, because they're all easy to overlook in the accounting of absences, and they're actually quite strange in their own right. The galaxies found inside the Boötes Void are not distributed evenly through the volume. They are not scattered across the full 330 million light-years the way you might expect if they were random survivors of some process. They sit in a roughly cylindrical arrangement, a tube running through the interior of the void. Later surveys have confirmed this shape multiple times, a tube of 60 galaxies inside a sphere of emptiness. The leading explanation for this arrangement is that the Boötes Void didn't form all at once from a single primordial underdensity. It may have formed from the merging of several smaller voids, maybe 4, maybe 7, the models vary, each void growing independently and then coalescing, the way soap bubbles coalesce, their shared walls disappearing, the interiors combining. And the tube of galaxies, that's the trace of those old boundaries. When two voids merged, The galaxies that had been sitting on the interface between them got folded into the interior. They didn't belong to either void exactly. They were the leftover material from the seams. The tube is a scar, and I'm less certain about their framing, so take it loosely, the tube is a record. A structural memory of how the void assembled itself, preserved in the positions of the galaxies that didn't quite escape to the edges. What's strange about 60 is partly the number itself and partly the distance between them. If you took 60 galaxies and spread them evenly through a sphere 330 million light-years in diameter, the average separation between any two galaxies would be roughly 10 million light-years. 10 million light-years between neighbours. Our nearest large galactic neighbour, Andromeda, is 2.5 million light-years away. So the average gap between galaxies inside the Boötes Void is 4 times the Andromeda distance. 4 times. In the rest of the universe, in normal regions of cosmic density, the average spacing between galaxies is a few million light-years. In galaxy clusters, it's far less, hundreds of thousands of light-years sometimes. The universe we live in, cosmically speaking, is not especially lonely. Galaxies exist in congregations. They pull at each other gravitationally, they interact, they merge over billions of years, they form the long filaments and dense nodes of the cosmic web. Inside the Boötes Void, each of those 60 galaxies is sitting in what amounts to profound solitude. Whatever gravitational interaction they have with their nearest neighbour is minimal. Whatever sense, if you can call it that, of belonging to a structure that a galaxy might have from the tidal forces and flows of its environment, absent, or nearly so. They're just sitting there in the quiet, evolving slowly without anything much to interact with. I keep coming back to 60, not because the number is inherently significant. It isn't, not really, but because it keeps doing something unexpected each time I approach it from a different angle. From one direction, it's an almost insultingly small number. From another, it's a genuinely puzzling one. Why 60 and not 0? If the initial density of the void was so low that 1,940 galaxies failed to form, what was different about the conditions that produced these 60? Were they sitting on the edges of the void, near the walls where density was slightly higher? Were they remnants of the pre-merger boundaries? Were they... And this is the question that actually doesn't have a clean answer. Just lucky, in whatever sense that word applies to physics. Maybe lucky is the wrong word. Maybe there's a better one, and I'm not landing on it right now. But the 60 feel like something. They feel like evidence of a process that was trying to run and mostly couldn't. Like the faint scratches on a surface that tell you something moved across it, even if the thing itself is long gone. 2000 would look like something you could describe from the outside, a region, a structure, a feature in the cosmic map with presence and weight. 60 is not that. 60 is quieter than absence. It's what's left when something doesn't happen, and what's left takes up almost no room at all. The space where 1,940 galaxies didn't form is still there. It takes up the same 330 million light-years, whether it's full or empty. The distance doesn't care about the density. The volume doesn't shrink because it's mostly unoccupied. And somewhere in that mostly unoccupied volume, in the dark between those 60 scattered, widely spaced, slowly evolving galaxies, is the actual question that this void is asking, not yet ready to be answered, just sitting there, in the quiet, waiting for us to build better telescopes and more patient theories and maybe a slightly different way of thinking about how a universe puts itself together. Start before galaxies. Start before stars. Before any of the structures we use to orient ourselves in the cosmic map, the filaments, the clusters, the voids themselves. Go back far enough and the universe is a different kind of thing entirely. Not empty. The opposite of empty. A hot, dense, churning plasma filling all of space, every point in space simultaneously, because space itself was smaller then and still growing. This is not a metaphor. The early universe was genuinely physically full, a wall-to-wall soup of matter and radiation so tightly packed that light couldn't travel more than a short distance before being absorbed and re-emitted. The universe was opaque, not dark. The plasma was glowing intensely in every direction, but impenetrable to the kind of light that carries information. Photons couldn't go anywhere without immediately hitting something. It was, in the most literal physical sense, a place where nothing could be observed from the inside. And into that opacity, into that smooth, hot, densely packed everywhere, there were fluctuations, small ones, almost embarrassingly small. The density variations in the early universe were on the order of 1 part in 100,000, 1 part in 100,000. If you took the average density of the early universe and called it 1.00000, then the overdense regions were something like 1.00001, and the underdense regions were something like 0.99999. The difference between a place that would eventually become a galaxy cluster and a place that would eventually become the Boötes Void was, in the beginning, a fluctuation you'd need extremely sensitive instruments just to confirm was real. These fluctuations were quantum in origin, which is to say they arose from the fundamental graininess of physical reality at very small scales. The irreducible jitter of quantum fields that can't be smoothed away because the uncertainty is built into the structure of things. During inflation, the period of extremely rapid expansion in the universe's first fraction of a second, these quantum fluctuations were stretched from subatomic scales to scales that eventually spanned millions of light years. The microscopic became macroscopic, the quantum became cosmic, and then the universe expanded and cooled, and the fluctuations were locked in, written into the distribution of matter like grooves pressed into something that then hardened. I want to stay here for a moment because I think this is where the Boötes Void actually begins, even though it won't look like anything for hundreds of millions of years. Somewhere in the early universe, in that nearly smooth plasma, in that 1 in 100,000 variation in density, there was a region that was slightly, almost imperceptibly, underdense. A patch of space where the matter was just a little thinner than average. Not enough to notice, not enough to matter in the immediate term. Just a whisper of deficit in the distribution. That whisper is old or born. It predates everything. It predates the first stars, the first galaxies, the first anything with structure. It is, in a sense, older than the universe has had time to properly process, which is one of the reasons the Boötes Void is as large as it is. What happens to an underdense region as the universe evolves is not complicated in principle, but it's slow. Gravity is the engine of structure formation, and gravity is patient in a way that nothing else in physics is. In the dense regions, matter pulls toward itself, the overdense patches attracting more matter from their surroundings, growing denser, eventually collapsing into the first stars and then the first galaxies. It's a feedback loop with no upper bound. Denser regions pull harder, pull more matter, become denser still, pull harder again. The rich get richer. Cosmologists actually use a version of that phrase, and in the underdense regions, the opposite. Matter drains away toward the denser patches. The slightly thin places become thinner. Their gravitational pull weakens as they lose mass, which means they pull less effectively on the matter at their edges, which means more matter leaves. The feedback runs the other direction. The poor get poorer. Over hundreds of millions of years, this process, running simultaneously in both directions across the entire universe, carved the cosmic web out of what was once a nearly featureless plasma. The dense regions became filaments and nodes. The underdense regions became voids. The structure emerged from a tug-of-war between patches of matter that differed initially by 1 part in 100,000. I was reading about this late one night and found myself staring at a simulation still frame, one of those false-colour density maps of the cosmic web, orange filaments on black. And what struck me, sitting there at the desk with the chair making that faint creak it always makes when I lean back, was how inevitable the structure looks in retrospect, like something that could only have turned out this way. The filaments connect in exactly the places they should connect. The voids sit in exactly the places where voids should sit. It looks designed almost, but it isn't. It's just gravity, running forward from nearly uniform initial conditions for 13.8 billion years. What a strange machine to produce all of this from almost nothing. But dark energy complicates the picture. And here's where it gets, I want to say interesting, but the word that actually fits is awkward. Because dark energy is the thing we invoke to explain observations we can't otherwise account for. And invoking something you don't fully understand in the middle of an explanation you're trying to make clean is always a little uncomfortable. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate, not just expand as accelerate. The galaxies are not only moving apart from each other, they're moving apart faster and faster over time, and the force or property or field responsible for this is dark energy, which makes up roughly 68% of the total energy content of the universe, and which we understand at the mechanistic level almost not at all. What dark energy does to voids is amplify them. In an underdense region, gravity is already weak. There's less matter, so less pull. But dark energy pushes, it acts on all of space equally, and its effect is more pronounced in low-density regions because there's less gravitational resistance to counteract the push. So voids expand faster than the average expansion of the universe. Their walls get pushed outward. The matter on the edges gets swept more efficiently toward the filaments. The interior gets emptier. Dark energy is essentially a thumb on the scale, pressing in favor of emptiness. Now, run this process. The drainage of matter toward dense regions, the accelerating expansion pushing void walls outward, the feedback loops in both directions. Run it for 13.8 billion years. Start with a fluctuation of 1 part in 100,000. What do you get? You get the cosmic web. You get superclusters and filaments and the great walls of galaxies that thread through the observable universe. And in the places that started slightly underdense, you get voids. Typical voids are 30 to 300 million light-years across. That's the range. Most fall somewhere in the middle. The physics produces them reliably, and the sizes the physics produces are consistent with what we observe across most of the sky. The Boötes Void is 330 million light-years in diameter, which puts it at the very top of the range, or possibly outside it, depending on who you ask and which model they're using. This is where the comfort of the explanation starts to thin. The process that forms voids is real and well understood. The outcome of that process, across most of the observable universe, is consistent with what cosmological simulations predict. But the Boötes Void is not sitting comfortably in the middle of those predictions. It's sitting at the edge or past the edge, and the question of whether the standard process, quantum fluctuations, inflation, gravitational feedback, dark energy, can plausibly produce something this large in the time available is one that cosmologists have been quietly arguing about since the 1980s. The current consensus is probably yes. Barely. barely is doing a lot of work in that sentence. One proposed mechanism that helps is void merging. The idea is that the Boötes Void didn't grow from a single primordial underdensity. Instead, several smaller voids, each growing independently from their own initial fluctuation, eventually merged. Their shared walls collapsed. The separate underdensities combined into one larger one. The merged structure inherited the size of the sum of its parts and then kept growing. This explains the tube of 60 galaxies running through the interior, which are thought to be the remnant material from the boundaries between the merging voids, the stuff that was on the seams, now folded into the interior of the combined structure. It's a tidy explanation. It has internal consistency, and it does bring the Boötes Void somewhat closer to what the standard model can comfortably produce. Somewhat closer. There's something I keep circling without fully landing on, which is that the model can accommodate this, and the model predicts this are different things. The Boötes Void is accommodated, it isn't predicted. No cosmological simulation run forward from standard initial conditions throws up a structure quite this large and quite this empty as a routine outcome. It appears, when it appears at all in simulations, as a rare fluctuation at the edge of what the model can generate. That's worth holding. The universe's best confirmed theory of large-scale structure can explain the Boötes Void, but only if you're willing to accept that it represents an unusually extreme outcome of a usual process, an outlier, a tail-end event. Whether that's satisfying depends, I think, on what you are hoping for from an explanation. The early universe, that smooth, hot, full plasma, didn't know it was going to produce this. There was no blueprint. There was just the quantum jitter, the inflation, the cooling, the slow pull of gravity across billions of years. The cosmic web assembled itself from those ingredients the way a crack assembles itself in drying mud. Following the physics, always following the physics, producing something that looks almost inevitable in retrospect but wasn't chosen. Somewhere in that process, somewhere in the long sequence from quantum fluctuation to inflated perturbation to growing underdensity to draining void to merging void to supervoid, the Boötes Void became what it is. 330 million light-years of mostly nothing. Grown from a whisper of deficit that was, in the beginning, smaller than anything we have language for. The sentence is not complicated. If the Milky Way had been in the centre of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Greg Aldering said it, astronomer, part of the team that catalogued 15 additional galaxies inside the void in 1989. One of the people who mapped the interior carefully enough to notice that the galaxies weren't scattered randomly but arranged in that strange tube. He said it as a way of conveying scale. A thought experiment in a single sentence. The kind of thing scientists sometimes produce when the numbers stop being adequate on their own and something more direct is needed. It works. It more than works. But I don't think it's only about scale. Here is what the sentence actually says if you follow it carefully. We discovered other galaxies, confirmed them, understood them as separate island universes, measured their distances in the 1920s. Edwin Hubble, Cepheid, variable stars, the Andromeda Galaxy resolved into individual stars and suddenly understood to be not a nebula inside the Milky Way, but a structure comparable to the Milky Way, sitting 2.5 million light-years away. 1923, 1924, the universe got very large very quickly in those years. Everything we'd thought was the totality of existence turned out to be one galaxy among many. Among billions, it would eventually emerge. That happened in the 1920s. If the Milky Way had been sitting at the centre of the Boötes Void, Aldering is saying it wouldn't have happened until the 1960s, 40 years later. A full generation of astronomy would have passed without the most basic fact about the large-scale structure of the cosmos. We would have had quantum mechanics and nuclear physics and the development of radio astronomy and the space race. All of that would have proceeded, but we would not have known with any certainty that the universe contained other galaxies. Think about what that means for what we would have believed about our place in things. The nearest galaxies to a Milky Way sitting at the centre of the Boötes Void would be at the void's edge, roughly 165 million light-years away, in the dense walls of galaxies that bound the emptiness. The Andromeda galaxy in our actual universe is 2.5 million light-years. The Large Magellanic Cloud is 160,000 light-years. These objects are, by astronomical standards, practically in the room with us. They are visible to the naked eye. Andromeda appears as a smear of light in the sky on a dark night, slightly larger in angular size than the full moon, though far too faint for most people to notice without knowing where to look. From inside the Boötes Void, there would be nothing like that. The nearest galaxy, whatever happened to be sitting on the interior edge of the void's wall, would be so distant that early telescopes couldn't have reached it. The photographic techniques of the 1920s that allowed Hubble to resolve Andromeda into individual stars would have been insufficient. The light would be there, technically, but too faint and too diffuse to disentangle from noise. And so the astronomers of that era, wherever they were in whatever version of the 1920s exists inside this thought experiment, would have looked out at the sky and seen the Milky Way. Stars, nebulae, the galactic plane, and at the edges, where Andromeda should have been smeared across the sky, just dark, just the faint glow of distant things too far away to resolve. They wouldn't have known what they were missing. You can't detect an absence you have no reason to expect. This is the part of Aldering's sentence that I keep returning to. Not the scale of the void, though that's real and genuinely hard to absorb, but the epistemic part, the knowledge part, the fact that what you know about the universe depends, in a very literal, non-abstract way, on where in the universe you happen to be sitting. We think of knowledge as something that accrues through effort and intelligence and the right instruments, and it does, but it also accrues through location, through the particular density of your cosmic neighborhood, through whether you happen to live in a filament or a void, in a supercluster or an emptiness, near enough to other galaxies that you can see them, or far enough that you can't. The astronomers inside the Boötes Void would not have been less intelligent than Hubble. They wouldn't have had inferior telescopes, assume the same technology, the same methods, the same careful work. They just would have been in the wrong place. The universe around them would have been giving them the wrong data. Not false data, accurate data about their local conditions, but data that systematically concealed the larger structure. I find this unsettling in a way that takes a moment to locate. It's not that I think we're in that position. I don't. The evidence for the large-scale structure of our universe is extensive and cross-confirmed across many methods. But the possibility that Aldering's thought experiment describes, that your location in the universe shapes and potentially limits what you can know about it, that possibility doesn't go away just because we happen to be in a good location. What if there's something else? Some larger structure, some feature of the cosmos that is simply beyond the horizon of our own position, something that astronomers in a different part of the universe would see clearly and we have no view of at all? What if we are, right now, in some different sense, exactly where those void astronomers were in the 1920s, working carefully, working accurately, but missing the thing we don't know to look for? I don't mean this as a license for speculation about hidden dimensions or anything like that. I mean it as a genuine epistemological question. the kind that the Boötes Void puts on the table whether you want it there or not. Where you are determines what you can see. What you can see determines what you think the universe is. The Milky Way, in actuality, sits in a reasonably dense part of the cosmos. We're on the outskirts of the Virgo supercluster, more recently understood as part of the larger Lonelier supercluster, in a filamentary region with enough bay-bursting galaxies that our galactic neighbourhood is, cosmologically speaking, active. Andromeda is close. The local group is populous enough to study in detail. We have, by some accident of initial conditions, ended up in a good place from which to observe the universe. Good for observation, I mean, not good in any other evaluative sense. The universe doesn't arrange itself for our benefit, and the fact that we landed in a spot with adequate visibility is just that. A fact, contingent, as arbitrary as any other aspect of our cosmic address. But it matters. It has shaped everything we know. The 1960s detail in Aldering's sentence is worth pausing on because it's specific. He didn't say much later or decades later. He said the 1960s, which means he was estimating, based on the size of the void, the distances to its walls, the capabilities of 20th century optical astronomy, roughly when telescopes and photographic techniques would have improved enough to reach the void's edge and resolve the galaxies there into identifiable structures. 40 years. In those 40 years, in our actual universe, between the 1920s and the 1960s, cosmology changed beyond recognition. The expanding universe was confirmed. The Big Bang model was developed. The cosmic microwave background was discovered in 1965, providing direct observational evidence for the early state of the universe. The age of the cosmos was estimated, revised, estimated again. A whole framework for understanding where we are in the history of things was built. In the void, that framework would have been built without one of its central inputs. The universe would have been correctly understood to be expanding. That's detectable from the redshifts of nearby stars and gas clouds. You don't need external galaxies for that. But the scale of what was expanding, the structure of what was out there, the web of filaments and clusters and supervoids that we now know constitutes the architecture of the cosmos, all of that would have been in the 1920s through the 1950s genuinely unknown. A different cosmology would have developed, based on real observations, using real methods, and containing a fundamental gap where the external universe should have been. What Aldering's sentence does, and I think this is why it stays with you after the initial scale impression fades, is make the universe feel contingent, dependent on the observer, shaped, at least in terms of what the observer can access, by the observer's position. The physics doesn't change. The galaxies at the edge of the Boötes Void are there regardless of whether you can see them. The void is real, regardless of whether anyone inside it understands what they're inside. The universe is not altered by the quality of the local view, but knowledge is. Human knowledge, or whatever passes for knowledge in any civilization anywhere, is local, assembled from local data, tested against local conditions, and the local conditions in the Boötes Void would have produced for a long time a cosmology with a significant blind spot built in. That's not a failure, that's just physics, that's just where they would have been. There's a moment when I think about this where I want to reach for some larger conclusion, something that wraps the thought up and gives it a satisfying shape. But I don't think it has one. Or at least, I haven't found it. The thought experiment is clean and the implications are real, and the unsettling quality doesn't resolve into something more comfortable. Where you are shapes what you know. The Boötes Void is, among other things, a demonstration of that in the starkest possible terms. And we are somewhere. We are always somewhere, And whatever we cannot see from here is not less real for being beyond the range of our instruments or our position or our era. That thought doesn't close neatly. It's probably not supposed to. The explanation exists. That's worth saying up front. Because with something like the Boötes Void, there's a pull toward treating the emptiness as permanently inexplicable as a thing that resists understanding by its very nature, and the pull is not accurate. There is a leading hypothesis. It has internal consistency. It aligns with what we know about how cosmic structure evolves, and it accounts, at least in broad terms, for most of what we observe when we look carefully at the void's interior. The hypothesis is that the Boötes Void is not a single void, or rather that it is now, but it wasn't always. The current leading picture of how it formed involves several smaller voids, each growing independently from its own initial underdensity, eventually merging into the structure we observe today. The shared walls between them, the thin filaments of slightly denser matter that once separated one void from the next, collapsed inward as the voids expanded, and what had been multiple separate absences became one larger, combined absence, inheriting the volume of all of them while losing the boundaries between them. This is where the soap bubble comparison comes from, and it's a good one, up to a point. If you've ever watched soap bubbles carefully, the kind that form when you're washing dishes or when children blow them in a garden, you'll have noticed what happens when two bubbles touch. The shared wall between them, the thin film of soap separating the two interiors, undergoes a specific geometry. It curves in a way that balances the pressure from both sides, and if the bubbles are similar in size, the shared wall is nearly flat. And then, if one bubble grows or the pressure shifts, that shared wall can disappear entirely. The two bubbles merge into one, the shared film gone, the combined interior now larger than either was alone. The physics that governs void merging is different from the physics of soap bubbles. Gravity rather than surface tension, dark energy rather than pressure differentials, timescales of billions of years rather than seconds, but the topological outcome is similar enough that the comparison has stuck in the literature, and it's stuck for good reason. When two voids merge, the shared wall of slightly denser matter, the galaxies and gas that had accumulated at the boundary between them, doesn't vanish. It gets folded into the interior of the new, larger void. It becomes an interior feature rather than a boundary feature. A remnant of what was once a wall, now floating inside the combined emptiness. And this is what the tube of 60 galaxies is thought to be. The tube running through the center of the Boötes Void, the roughly cylindrical arrangement of galaxies that subsequent surveys confirmed and remapped. That arrangement is the trace of the old boundaries. The seams of the former smaller voids, preserved in the positions of the galaxies that were sitting on those seams when the merger happened. They didn't escape to the walls of the new larger void because there wasn't enough time or enough gravitational pull from the walls to move them all the way out. So they stayed, roughly where the boundaries used to be, forming a structure that now looks like a tube, because the boundaries were themselves roughly tubular, or rather roughly planar. And when planar structures are folded and compressed by a merging event from multiple directions, what you get is something elongated, something that runs through the interior like a spine. The galaxies in the tube are, in this picture, not survivors of the void's interior so much as refugees from its former boundaries. They were boundary material that got left behind when the boundary ceased to exist. There is something almost specifically lonely about that, and I'm genuinely not sure if that's a real observation or just a projection, probably some of both. How many smaller voids merge to form the Boötes Void? The models vary. Some analyses suggest 4 to 7, which is a range wide enough to suggest that the precise number is not yet well constrained by the data. The merging process doesn't leave clean edges. By the time the voids have fully combined, the record of the individual components is largely erased, preserved only in things like the tube of galaxies and the overall shape of the density profile. Forensic cosmology in a way, working backward from the current state to reconstruct a history that no instrument directly observed. What the models do agree on is that void merging is a real and expected process. It isn't exotic or ad hoc. It follows directly from the same physics that produces individual voids in the first place. Smaller underdensities grow, expand, eventually contact each other, merge. The merge structure is larger than its components. Over enough time, and given the right initial conditions, you can build a very large void from a collection of more modestly sized ones. The question, and this is where I start to feel the explanation pulling in two directions at once, is whether you can build this void from that process, within the time available, starting from the kinds of initial density fluctuations that standard cosmological models predict. And the answer is probably. With the right configuration of initial underdensities, the right merging history, the amplifying effect of dark energy accelerating void expansion over the past several billion years, yes, probably. The Boötes Void is not ruled out by the merger hypothesis and the standard model of cosmology combined, but there's a quality to probably given the right conditions that is subtly different from this is what we'd expect. The merger hypothesis explains the Boötes Void without requiring any new physics, which is genuinely significant. It means we don't have to invoke anything exotic, anything outside the current framework to account for what we see. That's not a small thing. Most of the time in cosmology, when something looks anomalous, the eventual explanation turns out to be a known process at an unusual scale, and that's probably what's happening here. But the Boötes Void sits at the edge of what the known process reliably produces. The simulations that reproduce it most convincingly tend to do so in runs where the initial conditions happen to be particularly favourable. A cluster of several underdensities positioned just so, with just enough dark energy amplification over just enough time. It appears in simulations the way a large wave appears in a sea that is mostly producing smaller waves, genuinely as a product of the same physics, but not as something the physics was particularly aiming for. I found myself reading a paper on this, sitting on the floor actually, leaning against the couch, the kind of reading position that happens when you meant to sit properly and then got absorbed before you adjusted. And what struck me wasn't the math, which I was moving through slowly and incompletely, but a single phrase in the discussion section, something like, consistent with lambda, CDM at the 2 sigma level, which means consistent, which means allowed, which means the model doesn't forbid it. 2 sigma is not a comfortable margin for something this large. The soap bubble comparison, to return to it briefly and then let it go, does something useful and something slightly misleading. The useful thing, it conveys the process cleanly. Bubbles merge, boundaries disappear, combined interiors form. The slightly misleading thing, soap bubbles merge quickly, visibly, with an audible pop if you watch carefully. The merger of voids happens over hundreds of millions of years, across distances that light takes millions of years to cross, through a process so gradual that nothing inside the voids would experience it as an event. There is no moment of merger. There is just the slow recession of boundaries, the slow expansion of interiors, the slow loss of the distinction between one emptiness and another, which makes the soap bubble comparison useful as a topological guide and inadequate as a physical one. Real bubbles have surfaces you can touch and thin, iridescent, fragile, the kind of thing that breaks if you breathe on it wrong. The walls between voids are filaments of galaxies spanning tens of millions of light years, threaded with dark matter, glowing with the light of billions of stars. They're not fragile. They just lose eventually to the apparition, the void growing from within, the wall retreating, the interior widening 1 megaparsec at a time, until the wall is gone and there's only the expanded empty inside. Soap bubbles, but slower, darker, and with no one watching when the wall disappears. What the merger hypothesis doesn't fully explain, and this is the part that leaves the chapter feeling unfinished, because it is genuinely unfinished, is why the initial underdensities that eventually merged into the Boötes Void were clustered together in the first place. Voids don't merge unless they're near each other. Several voids merging into one large supervoid requires that several independent underdensities happened to develop in roughly the same region of the early universe, close enough that their expansion eventually brought them into contact. Is that unusual? Is it the kind of clustering of underdensities that the standard model readily produces? Or is it itself a somewhat unlikely configuration? The honest answer is that this depends on the model parameters you're using, and different analyses produce different assessments of how improbable the initial conditions would need to have been. Some papers argue the configuration is within normal statistical variation. Some argue it requires a somewhat extreme tail of the initial density distribution. None argue it's impossible. Which leaves the Boötes Void in this specific, slightly uncomfortable position, fully explainable, technically consistent with everything we know, and still sitting at the far edge of what we'd consider routine. An outcome that the universe's physics permits but doesn't particularly favour. Something that could happen and did and remains, even after 40 years of study and multiple surveys and the best available cosmological simulations, not entirely comfortable to fully account for. The explanation holds. It just holds the way something holds when it's doing its best under conditions it wasn't quite designed for. Steady but not effortless. Sufficient but not clean. And the 60 galaxies in their tube through the centre of the void remain where they are. Stranded inside the merged interior, remnants of a boundary that no longer exists, evolving in solitude at distances from each other that make the word neighbour feel almost ironic. A photon leaves a galaxy, not a galaxy inside the Boötes Void. There are too few of those, and they sit in their tube in the interior, largely isolated. This photon leaves a galaxy on the wall of the void, one of the dense filaments that bound the emptiness, where galaxies cluster in the usual way, where the cosmic web is doing what it does in most of the universe. A star in that galaxy, in some unremarkable moment of nuclear fusion, releases a photon. The photon travels outward through the galaxy, through the sparse intergalactic medium at the galaxy's edge, and then it reaches the boundary of the Boötes Void. And it enters. What it enters is not nothing. This is worth being precise about, because the word void implies a completeness of emptiness that the physics doesn't actually support. The Boötes Void contains matter, just far less than average. The density of matter inside it is estimated at somewhere around 10 to 15% of the cosmic mean. So there are atoms in there. There is dark matter, diffuse and structured into faint filaments too thin to host many galaxies. There are the 60 known galaxies in their tube. There is gas, sparse and cold between them. The void is underdense. It is not a perfect vacuum. But for a photon crossing it, the difference from vacuum is negligible. The photon moves at the speed of light, as photons do, as photons must, and it begins the crossing, The crossing will take approximately 330 million years. In those 330 million years, the universe does not sit still. This is the part that matters, and it takes a moment to properly set up. The universe is expanding, not into anything, there's no outside for it to expand into, but space itself is stretching. The distance between unbound objects increasing over time, the metric of the cosmos changing as it ages. This expansion has been happening since the beginning. For the last several billion years it has been accelerating. Driven by dark energy, the universe's expansion is not slowing under gravity the way early cosmologists expected. It is speeding up. The rate of separation between distant objects growing larger with time. Now, the photon enters the void. At the moment it enters, it is crossing into a region of lower density than the surrounding universe. Lower density means weaker gravity. And gravity, this is the part to hold, gravity shapes the geometry of space. In regions of higher density, the gravitational potential is deeper. In regions of lower density, it is shallower. The transition from a dense filament into the interior of the Boötes Void is, in the language of general relativity, a transition from a deeper gravitational potential well to a shallower one. To enter the void, the photon climbs. Climbing costs energy. For a photon, energy is frequency. Higher frequency means higher energy, lower frequency means lower energy, and a photon that has lost energy has shifted toward the red end of the spectrum, toward longer wavelengths. Gravitational redshift is real, measurable, confirmed in laboratories and in astronomical observations. Photons that climb out of gravitational wells lose energy. They redshift. The effect is small for shallow potential differences and large for deep ones. When a photon climbs from the dense wall of the Boötes Void into the void's interior, it redshifts slightly. It loses a small amount of energy to the gravitational climb. In a static universe, a universe that was not expanding, whose gravitational potentials were not evolving over time, this would be the whole story, and it would be boring. The photon climbs into the void, losing energy. Then it crosses the void and climbs back out the other side into the dense filament on the far wall, and it gains energy, descending back into the potential well. The energy lost on entry is recovered on exit. The photon arrives at the far wall with the same energy it had when it left. Net effect, 0. But the universe is not static. While the photon crosses the void, while it spends 330 million years traversing that under-dense interior, the void itself is changing. Voids grow. They expand faster than the average expansion of the universe because dark energy's accelerating effect is least counteracted in low-density regions. The walls of the Boötes Void are very slowly receding from each other. The interior is getting larger. The gravitational potential inside is getting shallower. The void is, in a sense, flattening as the photon crosses it. And here is the consequence, and it is a real one. When the photon reaches the far wall and begins its descent back into the dense region, begins to recover the energy it spent climbing in, the potential well it is descending into is slightly shallower than the one it climbed out of on the other side. The hill it is going down is not as tall as the hill it came up. The universe expanded while the photon was crossing, and the expansion changed the geometry the photon was moving through. The photon exits the void with less energy than it entered with. I've had a cold cup of tea sitting next to me for the last hour, the kind of lukewarm that is worse than cold because it still has the smell of tea but none of the point, and I keep picking it up and putting it back down while trying to get this next part right, because the next part is where the physics gets formally named, and I want to arrive at the name having already understood what it describes. What just happened to the photon has a name. It is called the integrated Sachs-Wolf effect. The integrated part refers to the fact that the effect accumulates over the entire crossing. It isn't a single event, but the sum of small energy changes experienced by the photon throughout its journey, integrated across the full path. Sachs and Wolf were the physicists who worked out the theoretical framework for how changes in gravitational potential affect photons traveling through the cosmos. The effect is real, it is confirmed, and it is one of the few ways that the large-scale structure of the universe leaves a fingerprint on the oldest light we can observe. That oldest light, the cosmic microwave background, is the radiation left over from roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could finally travel freely. It fills the sky uniformly at a temperature of about 2.7 Kelvin, with tiny fluctuations of a few hundred millionths of a degree. Those fluctuations carry enormous amounts of information about the early universe. And one of the things that can alter them, can imprint additional temperature variations on top of the primordial ones, is the integrated Sachs-Wolf effect. Photons from the cosmic microwave background that happen to pass through a large void on their way to our detectors lose a small amount of energy to the ISW effect and arrive slightly cooler than they would have otherwise. The Boötes Void is large enough and empty enough that it should produce a detectable ISW imprint on the CMB. Whether that imprint has been clearly identified is complicated. The CMB cold spot, a region of the cosmic microwave background that is anomalously cold, detected first by WMAP and later confirmed by the Planck satellite, is not in the direction of the Boötes Void. The cold spot sits in the constellation Eridanus, and the supervoid most associated with it is the Eridanus supervoid, which is a separate structure and a much larger one, roughly 1.8 billion light-years across, discovered in 2015. The Boötes Void and the CMB cold spot are not the same story, but the physics connecting large voids and CMB temperature anomalies is the same physics. The ISW effect operates on any photon passing through any sufficiently large, sufficiently deep underdensity. The Boötes Void is large enough and empty enough to produce a real, if modest, ISW signature. And this means it is not just an absence in the galaxy distribution, it is an active structure, a region that is doing something measurable to the light that passes through it. The void touches the photons that cross it. They leave changed, subtly, permanently carrying the void's signature in their reduced energy. There is something about this that I find genuinely hard to put down. The idea that emptiness has a physical effect. That passing through a region where almost nothing exists still costs something. The photon arrives at its destination, wherever that is, whatever detector or telescope eventually catches it, carrying less energy than it would have carried if it had travelled the same distance through an average density region. The void has marked it, not metaphorically, physically. The absence did something, the nothing exerted itself. And if you point a sensitive enough instrument at the right part of the sky and look at the temperature of the CMB photons coming from that direction, photons that may have crossed through or near the Boötes Void on their way to us, you are, in a very real sense, reading the void signature, measuring the energy it extracted from the light that passed through it. An empty region of space 330 million light-years across that left its mark on photons that were already 13.8 billion years old when they entered it. The crossing takes 330 million years at the speed of light. The energy loss when it arrives is a few millionths of a degree. Small, precise, and entirely real. They are not survivors in any dramatic sense. Survival implies a threat that was navigated, something that came close and was avoided. These 60 galaxies inside the Boötes Void did not survive anything. They simply formed in a place where the usual conditions for galaxy formation were barely met, and they have been evolving there ever since, in the quiet, in the wide spacing, in the near total absence of everything that makes the rest of the universe feel busy. They didn't outlast something, they just grew slowly in a very large empty room, without much happening around them. That distinction matters, I think, though I'm not entirely sure why it feels important enough to start here. The physical conditions inside the Boötes Void are real and measurable, and they're different from the conditions that most galaxies experience. In a normal region of the universe, in a filament, near a cluster, in the kind of environment the Milky Way inhabits, a galaxy is embedded in a web of gravitational influence. Neighbouring galaxies pull at it tidally. Occasionally they pass close enough for their mutual gravity to distort their shapes, trigger starbursts, funnel gas inward, heat or strip the interstellar medium. Clusters subject their member galaxies to ram pressure stripping, the hot intra-cluster gas acting like a headwind as the galaxy moves through it, physically removing the galaxy's own cold gas reservoir, quenching star formation. Mergers happen. Interactions are routine. None of this happens inside the Boötes Void, or happens only in the most attenuated form. The average separation between the 60 galaxies in the void is roughly 10 million light-years. 10 million light-years between neighbours. At that distance, tidal forces between galaxies are negligible. The gravitational influence each one exerts on the others is so weak across such a large gap that interactions in any meaningful dynamical sense simply don't occur. Each galaxy in the void is evolving in something close to genuine isolation, shaped almost entirely by its own internal physics rather than by its environment. What does isolation do to a galaxy over billions of years? The answer, and this is where the science becomes genuinely interesting in the careful way that things become interesting when you study them closely enough, is that isolation preserves. It preserves gas. It preserves structure. It slows the pace of change. In dense environments, galaxies are constantly being acted upon, and the constant action tends over time to use up a galaxy's cold gas reservoir, the raw material for new stars. Ram pressure stripping removes gas directly. Tidal interactions heat gas, making it harder for it to cool and collapse into stars. Mergers can trigger intense starbursts that burn through gas reserves quickly. The result, in dense environments, is that many galaxies, particularly ellipticals and clusters, are largely done forming stars. They used up their gas, or had it taken away, and now they're mostly old stars slowly cooling. Void galaxies hold on to their gas. Without the stripping, without the heating, without the mergers and the starbursts, the cold gas that would otherwise have been removed or consumed just stays. It sits in the disk of the galaxy, available. And available gas means continued star formation. Slow, steady, ongoing star formation at a rate more like a long exhalation than the sudden gasp of a merger-triggered starburst. The observational evidence for this is in the colour. Galaxies that are actively forming stars appear bluer. The young, massive hot stars that dominate recently formed stellar populations emit strongly in the blue and ultraviolet. Galaxies that have stopped forming stars appear redder. The massive blue stars die quickly, leaving behind only the longer-lived, cooler, redder stars. Red galaxies are, in a real sense, older in their stellar population. Blue galaxies are younger, or at least still producing new generations. Surveys of galaxies inside the Boötes Void and similar voids have found a dominant fractions of bluer galaxies. The void's galaxy population skews blue in ways that correlate with ongoing star formation, with the presence of cold hydrogen gas, with the slower, steadier rate of stellar production that comes from an undisturbed gas reservoir. One study measuring star formation rates of galaxies in the Boötes Void region found rates ranging across a wide spread, with a median suggesting genuine ongoing activity, not the explosive activity of a merger, but the quiet, persistent kind. There is a study, Wegener, Salzer and colleagues working from the KPNO International Spectroscopic Survey, that looked specifically at star-forming galaxies in and around the Boötes Void, tracking both metallicity and star formation rates as functions of local density. What they found, somewhat against their expectation, was that the galaxies inside the void had properties nearly identical to a matched comparison sample from denser regions when corrected for stellar mass. The environment, being inside the void versus outside it, didn't seem to dramatically alter the fundamental processes of star formation, once you accounted for the fact that void galaxies tend to be less massive, which raises its own set of questions. If isolation doesn't change the physics of how a galaxy forms stars, just the rate, the timing, the gas supply, then what exactly is the void doing to these galaxies? What is 40-some billion years of solitude? I mean, more like 13 billion, but in galactic terms a very long time, actually producing? Something I keep coming back to, and I'll admit I don't have a clean answer for it. There should be more dwarf galaxies inside the Boötes Void than we find. This is a known tension in the field, and it applies to voids generally. The standard lambda CDM model predicts that voids should be full of small, faint, low surface brightness dwarf galaxies, below the detection thresholds of many surveys but present in large numbers. The gravitational physics that forms large galaxies should also produce many smaller ones, and in a void, where there are no interactions to disrupt them, no larger galaxies to cannibalize them, those dwarfs should accumulate over time. They're not there, or not in the numbers predicted. Whether they're genuinely absent or simply too faint for current surveys to reliably detect is unsettled. Deep imaging in ultraviolet and optical bands can reach magnitudes fainter than 22, which helps, but the void galaxies are often low-surface brightness objects. Their light spread across a large angular extent, diluted, hard to pull out of the background. The Dark Energy Spectroscopic Instrument, DESI, is helping with this. Its low redshift catalogues provide better volume sampling and improved sensitivity to faint sources. But as of now, the dwarf deficit in voids remains one of those quiet tensions in the model, present enough to be noted, unresolved enough to be still noted. The tube of 60 galaxies, that cylindrical arrangement running through the void's interior that we've discussed from the perspective of the merger hypothesis, looks different when you approach it from the perspective of the galaxies themselves. From the outside, it's a structural trace, a scar of former boundaries. From the inside, it's a neighborhood. The closest thing to a neighborhood that exists in the Boötes Void. 10 million light-years between neighbors is not a neighborhood in any sense that the word usually implies. I'm sitting here, window half open, the particular white noise of a late evening settling in, thinking about what 10 million light-years of separation actually means socially, if it means anything at all. Light from one of those galaxies to the nearest other takes 10 million years. Any information exchange between them, any gravitational signal, any light, any causal influence at all, crosses that gap at the fastest speed physics permits and still takes 10 million years. They are neighbours the way two cities on opposite sides of a continent might be neighbours. Technically close relative to the full scale of the void, practically isolated in every functional sense. What these galaxies offer science is something the dense universe can't easily provide. A control condition. In a laboratory experiment, you want a sample that has been subjected to the variable you're testing and a control sample that hasn't. Most of cosmology lacks this. The universe is one universe. You can't run it twice with different conditions. But void galaxies are as close to a control as galactic astronomy gets. They're the same basic objects as galaxies in filaments and clusters, formed from the same physics, but they've been sitting undisturbed for billions of years, evolving without environmental interference. Studying them, their star formation rates, their gas content, their metallicity, their morphology, gives cosmologists a baseline, a picture of what a galaxy becomes when it is left entirely to itself. And comparing that to galaxies in denser environments reveals what the environment has been doing, what the interactions, the stripping, the mergers, the constant gravitational noise of a busy neighborhood actually contributes to galactic evolution over cosmic time. The void galaxies are not special because something dramatic happened to them. They're tractable precisely because almost nothing did. And so they sit in their tube, these 60 galaxies, bluer than average, gas-rich, slowly forming stars, widely spaced, undisturbed, and they evolve at a pace that the rest of the universe mostly doesn't permit anymore. The universe is old enough now that most of the dramatic processes of galaxy formation have slowed. The merger rate is lower than it was. The star formation rate across the cosmos has declined significantly from its peak several billion years ago. Things are quieter everywhere now, relative to what they once were. Inside the Boötes Void, they were always quiet. The galaxies there never had a loud phase or had one only mildly. They have been doing the slow version of galactic life since they formed, and they are still doing it. And they will probably keep doing it for a very long time. In the wide dark between the void's walls, in the 10 million light-year gaps between each other, in the specific solitude that comes from having formed in a place where the universe, for whatever reason, simply chose not to fill. The official position is clear. The existence of the Boötes Void does not conflict with the lambda cold dark matter model of cosmological evolution. This is stated plainly in the literature, repeated in review papers, confirmed by multiple independent analyses. The standard model of cosmology, built on cold dark matter as the scaffolding of large-scale structure, a cosmological constant driving accelerated expansion, quantum fluctuations from inflation as the seeds of everything, can produce a void the size of the Boötes Void. It doesn't forbid it. It doesn't require exotic physics to accommodate it. The void sits inside the model, the way an unusual but legal move sits inside the rules of a game. Permitted, not prohibited, not particularly encouraged. This should be more comforting than it is. The distinction I keep pulling at, and I realise this might be a distinction that only bothers certain kinds of minds, so I'll try to be fair about it, is between a theory that explains something and a theory that predicts something. These are not the same. A theory that predicts an outcome before the outcome is observed is doing something epistemically stronger than a theory that accommodates an outcome after it's been found. Both are valuable. Both are part of how science works, but they carry different weight, and conflating them quietly flattens something important. Lambda CDM did not predict the Boötes Void. Nobody running cosmological simulations in the late 1970s was expecting Kirshner's team to find a spherical absence 250 million light-years across, the initial estimate, later refined upward, when they looked in the direction of Boötes. When the void was discovered, it was a surprise, a significant one. The theoretical framework of the time had no obvious slot for it. The subsequent decades of work have found ways to fit it in. The merger hypothesis, the role of dark energy in amplifying under densities, The statistical argument that rare large voids are tail-end outcomes of normal processes, and those ways are real. The fitting is genuine, but fitting something in after the fact is not the same as having anticipated it. What does it mean, precisely, for the Boötes Void to sit at the 2 sigma edge of what lambda CDM produces? In statistics, sigma refers to standard deviation, a measure of how spread out a distribution is around its mean. 1 sigma captures roughly 68% of outcomes in a normal distribution. 2 sigma captures about 95%. A 2 sigma result sits in the outer 5%. It is unusual. It is not impossible. It is the kind of thing that, in a large enough sample, you expect to find occasionally just from the normal spread of outcomes. The observable universe is large. There is only one Boötes Void that we know of in the volume we can survey, which means we have a sample size of 1 when it comes to structures of this particular scale and emptiness. With a sample size of 1, it is genuinely difficult to say whether the Boötes Void represents a 2 sigma fluctuation in a well-behaved distribution or an indication that the distribution has a heavier tail than the model predicts. That very large voids are more common than lambda CDM expects, suggesting something the model is missing. You cannot distinguish between those 2 possibilities from a single data point. You need either more voids of comparable size, which would suggest the distribution is different from predicted, or a confirmed absence of other such voids across the full observable volume, which would suggest the Boötes Void is genuinely a rare outlier in an otherwise well-described distribution. The data right now doesn't clearly deliver the verdict. I spent an afternoon going through a ResearchGate paper, one of those papers that is formally a preprint, carrying that particular quality of being simultaneously rigorous and slightly provisional, that specifically tried to evaluate the Boötes Void as a probe of primordial structure formation. The authors ran through the standard merger scenario, computed density contrasts, looked at what early dark energy models and warm dark matter variants would predict. I remember reading it at a table near a window, watching someone's dog pace back and forth on the pavement outside in a way that seemed to have nothing to do with anything, and thinking, these authors are doing something genuinely careful, which is acknowledging that the void is an outlier and trying to use it constructively, rather than just noting the anomaly and moving on. The paper's conclusion, and I'm paraphrasing, not quoting, was that the Boötes Void provides a sensitive probe of high redshift structure formation precisely because it sits at the edge of what standard models produce. Its extremity is what makes it useful. If you want to test whether early dark energy or non-Gaussian primordial fluctuations or warm dark matter leave observable signatures in a large-scale structure, the Boötes Void is the kind of object you should be looking at carefully. It's where the model's predictions are most stretched. It's where the signal to noise, in terms of discriminating between standard and non-standard cosmologies, is potentially highest. An outlier in that framing is not a problem to be explained away, it's a diagnostic. Here is the thing that sits uneasily alongside that framing though. Models can absorb outliers almost indefinitely by adjusting parameters. This is a known issue in cosmology. Lambda CDM has parameters, and those parameters can be tuned within observational constraints, and within that tuning there is often enough room to accommodate things that look, at first, like they shouldn't fit. The Hubble tension, the disagreement between early universe and late universe measurements of the expansion rate, is a current example of an anomaly that the model has been absorbing with varying degrees of comfort for years. Early dark energy is one proposed resolution. Modified gravity is another. Local void models are another. None has definitively closed the question. The Boötes Void is not the Hubble tension. It is a different kind of anomaly, less statistically sharp, less actively contested. But the pattern is recognizable. Something sits at the edge of what the model produces, multiple explanations within the model are offered, none is definitive, and the anomaly continues to be technically accommodated while remaining genuinely unexplained in the deeper sense. This is not a criticism of lambda CDM. The model is, by any reasonable measure, the most successful framework for understanding the large-scale structure of the universe that has ever been constructed. Its predictions of the CMB power spectrum, of baryon acoustic oscillations, of the large-scale distribution of matter, are confirmed to extraordinary precision. Calling it into question over a single large void would be a significant overreaction. But accommodation is not explanation, and the Boötes Void has been accommodated for over 40 years, without anyone being able to say with real confidence exactly how it got to be this large, this empty, this spherical, this soon after the Big Bang. There's a related question that comes up occasionally and then gets quietly set aside, whether the Boötes Void is actually a single coherent structure or an overlapping set of smaller voids whose combined effect creates the appearance of one larger supervoid in redshift surveys. Redshift space distortions, and the way peculiar velocities of galaxies distort their apparent positions when you use redshift as a distance break, can in principle make structures look larger or differently shaped in redshift space than they are in real space. The Boötes Void's boundaries as mapped in redshift surveys may not correspond exactly to its boundaries in three-dimensional physical space. Some analyses have suggested the void might be somewhat smaller in real space than redshift surveys imply. Some have suggested it is genuinely as large as it appears. The uncertainty in this is real, and it matters for how much of a problem the void poses for the model. A somewhat smaller void is somewhat less difficult to accommodate than the full 330 million light-year figure, but even the conservative estimates leave something large enough to be unusual. Even adjusted downward, the Boötes Void is at the edge of what routine structure formation produces. The adjustment changes the degree of the problem, not the existence of it. What bothers me, and I want to be precise about what I mean by bothers, because it is not the emotional register of distress. It's more like the intellectual register of something that doesn't sit flat, is the way the phrase consistent with lambda CDM can function as a conversation ender, when it might more honestly function as a conversation opener. Consistent with is a low bar. Almost anything that doesn't violate the model's core equations is consistent with lambda CDM if you're willing to accept that the initial conditions happen to be unusual. The question worth asking, and the question that the Boötes Void keeps putting back on the table, is whether we have a principled reason to expect initial conditions unusual enough to produce this void, or whether we are simply accepting that they were unusual because the void exists and must therefore have come from somewhere. That's circular reasoning, technically. Not fatally so science works circularly in certain respects, using observations to constrain theories and theories to interpret observations. But it's worth naming the circularity rather than hiding it inside the phrase consistent with the standard model. The Boötes Void remains classified as an acceptable anomaly. That classification is correct as far as it goes. It is acceptable. It does not require us to abandon the framework that has correctly predicted so much else. The merger hypothesis is reasonable. The dark energy amplification is real. The statistical argument that rare events occur in large universes is valid. And yet the void is 330 million light-years across, sitting at the edge of what the model comfortably generates, discovered by accident in 1981, studied for over 40 years, and still not fully explained in the sense that would make a careful scientist feel they have actually closed the question. Acceptable anomaly. Both of those words are doing real work. The anomaly is genuine. The acceptance is also genuine, earned, not merely asserted, based on real analysis. The two sit together in some tension, and that tension has not resolved and might not resolve for some time, depending on what future surveys find and what the next generation of cosmological simulations produces. The void doesn't care about the classification, it is what it is, at 700 million light-years from here, going about whatever it is that a supervoid does, which is mostly expanding very slowly into the surrounding structure, getting incrementally larger and incrementally emptier as dark energy pushes its walls outward and gravity continues its patient work of pulling matter away from the inside toward the dense filaments at the edges. It will be larger next year than it is this year, by an amount so small that no instrument we have could measure the difference in a human lifetime, but larger. The map exists, that's worth beginning with, because it's easy to forget, given everything, that the Boötes Void is not a theoretical construct, not a gap in the data that might be filled in by better instruments, not an artifact of the way redshift surveys project three-dimensional space onto two-dimensional charts. It is a mapped structure. Multiple surveys, across multiple decades using different instruments, different methodologies, different teams in different countries, have all returned to the same region of the sky and found the same thing. The void is there. Its boundaries are approximately known. Its interior has been catalogued, most 60 galaxies arranged in their tube, sitting in their wide spacing, and the cataloguing has been checked and rechecked. The map is real, and the map shows a hole. At right ascension 14 hours 50 minutes, declination 46 degrees, 700 million light-years from Earth, there is a roughly spherical region of space 330 million light-years across that contains approximately 3% of the galaxies it should contain, given what we know about how matter distributes itself across the universe. This is a fact. It will still be a fact tomorrow. Right now, not metaphorically actually, right now while you are reading this, or listening to it, or lying in the particular way you lie when something is playing quietly and you've stopped tracking the ceiling, the Boötes Void is expanding. The dark energy that pervades all of space is pushing its walls incrementally outward. The filaments and superclusters that bound it, the Hercules superclusters on its near edge, are not moving dramatically, not rushing away, just drifting, millimeter by cosmological millimeter, slightly farther from the void center than they were a moment ago. The galaxies inside the tube are aging. Their stars are burning. Their gases slowly, steadily forming new stars at the quiet rate that isolation allows. The photons crossing the void's interior are losing small fractions of their energy to the integrated Sachs-Wolf effect, arriving at the far wall infinitesimally cooler than they entered. All of this is happening at distances and timescales that make the word happening feel almost wrong, but it is happening. The void is not a memory or a historical record. It is a current condition of the universe, a present tense feature of the cosmos, ongoing. The light that left the void's edge when Kirshner's team was doing their survey in 1981 in whatever ordinary room the data was being processed in. That light has been travelling toward us since before the survey happened. The look-back time is 700 million years, which means the photons carrying information about the void's current state set out 700 million years ago, and will not arrive for another, well, the math is uncomfortable. The void's present, as it exists at this moment, will not be observable from Earth for 700 million years. Whatever civilizations are doing astronomy at that point, if any, we'll be seeing the void as it is tonight, as it is while you are trying to sleep. There is something in that which I find genuinely hard to sit with, and I don't entirely know why. The delay between existence and observation is a feature of all cosmological science, not unique to the Boötes Void. Every object we observe in the past. The sun we see is 8 minutes old. Andromeda is 2.5 million years old in our sky. The CMB is 13.8 billion years old. Delay is built into the physics of observation, written into the speed of light, inescapable. But with the Boötes Void, the delay feels different. Maybe because the void is defined by absence, and absence is harder to assign to a particular moment. The presence of a galaxy can be located in time. It was there, at that distance, when that light left. The absence of 1,940 galaxies is harder to pin. The void has been absent for the entire 700 million years the light has been travelling, and it was absent before that, and it will be absent when the light that's leaving now finally arrives at whatever is here to receive it. The void's defining feature is continuous. It doesn't flicker. 40 years of study have closed some questions and left others exactly where they were. We know the void is real. We know it is roughly spherical. We know its interior contains 60 galaxies in a tube-shaped arrangement, and we have good reasons to think that arrangement traces the seams of a merger history. We know the merger hypothesis is the leading explanation for the void's size and is consistent with the standard model of cosmology, consistent at the outer edge of what the model comfortably generates, but consistent. We know that dark energy played a role in the void's growth and is still playing it. We know the void leaves an imprint on light that passes through it, via the integrated Sachs-Wolf effect, and that this imprint is in principle measurable. We know the galaxies inside it are bluer than average, gas-rich, slowly star-forming, poorly understood in their dwarf population. What we don't know, and this is the part that has not moved much despite everything, is exactly how the void got to be this large within the time available since the Big Bang, with the kinds of initial conditions that the standard model predicts. The explanation is probably right. The numbers probably work, probably and barely keep appearing in the same sentence, and after 40 years, that's still the most honest thing to say. The question mark at the end of Kirshner's 1981 paper title has never been formally removed. One of the things the Boötes Void does, quietly without announcing it, is make the Milky Way's location feel specific in a new way. We are in a filament. We are in a region of the universe that is, by cosmic standards, reasonably full. Part of the Laniakea supercluster, embedded in a web of gravitational structure that gives us dozens of neighbouring galaxies within a few million light-years, that has made us, for all of human history, observers inside a populated universe. The night sky from Earth is full in the way that makes you feel surrounded, accompanied, part of something dense with light and matter. From inside the Boötes Void, the night sky would be nearly empty. The same physics, the same laws, the same fundamental constants, but the view almost unrecognizable. A civilization there would look out at darkness and see, at the very limit of their instruments, the faint smear of galaxies on the void's walls, hundreds of millions of light years away. Everything we take for granted about the populated universe, the sense that there is always more, always further, always another galaxy in another direction, that would not be obvious from inside the void. It would have to be inferred, worked out from first principles, believed before it could be confirmed. We are lucky in the most specific and non-sentimental sense of the word to be where we are. Absence teaches things that presence can't. This is not a mystical observation, it is a practical one. The Boötes Void teaches us about galaxy formation by showing us where it mostly didn't happen. It teaches us about the cosmic web by showing us its interior, the spaces the web was built to surround. It teaches us about dark energy by showing us a structure whose size reflects dark energy's long-term amplifying effect on underdensities. It teaches us about the limits of the standard model by sitting at those limits, persistently for 40 years, being accommodated without being fully digested. An absence this large has to be explained, and the explaining the 40 years of surveys and simulations and papers and revised estimates and dwarf galaxy puzzles and ISW calculations has told us a great deal about the universe that the presence of 2,000 ordinary galaxies in that region would never have revealed. The void is doing work. Scientific work, slow and ongoing, the kind that doesn't resolve cleanly but accumulates. The 60 galaxies in their tube are part of that work. The shape of the void is part of it. The question mark in the 1981 paper is part of it. Every instrument pointed at that region of the sky has been part of it. And the instruments are still being pointed, and the data is still coming in, and the picture is, slowly, incrementally, without drama, getting more detailed. There is a version of this story that ends with the void explained, the question mark finally removed, the merger hypothesis confirmed in precise detail with a complete accounting of the initial conditions, and the merger history and the dark energy contribution and the exact number of progenitor voids. Maybe that version exists somewhere in the future, when the next generation of surveys has mapped the void's walls with enough precision to reconstruct its history, when simulations are good enough to isolate the exact configuration of initial conditions that produced it. I find, sitting with this, that I'm not sure I want that version. Or, and this is the part I want to be honest about, I'm not sure the explained version would feel like a different thing from what I have now, because the void would still be there. 330 million light years of mostly empty space, expanding slowly, the 60 galaxies aging in their wide spacing, the light still crossing it and losing energy, the dark still being what it is. The explanation would tell us how it happened. It wouldn't change what it is. What it is the universe at its most spare. The cosmos having done the opposite of what it does most of the time, which is fill in, accumulate, build up into the structures that light up the sky. Here it drained instead. Here the matter left and didn't come back, or never quite gathered in the first place, and what remained is this, a volume of space that the universe made room for, without filling. If something about this settled somewhere in you tonight, if the void left something behind after all this time spent in it, the quietest way to carry it forward is to share it with someone else who might need a night like this. A subscription, a shared link, a single recommendation to someone who sleeps better with physics in the background. That's all. That's how this space stays open. The void will be slightly larger tomorrow than it is tonight, by an amount nothing can measure, and the 60 galaxies will be exactly where they are, in their tube, in their spacing, forming stars at their quiet rate, in the dark between the void's walls, in the specific and unrepeatable silence of a place where the universe, for some reason that we're still working out, chose not to fill. The map shows a hole. The hole is still there.